Hello, in this video I'm going to work through several proofs using math induction and number theory. Our first example relates to the Fibonacci sequence, and I've got the Pascal's triangle here, which on its diagonals has the Fibonacci numbers. What most people don't know, or what many people don't know, is the sum of the rows here, the sum of the digits in the rows, is equal to 2 to some power. Right? And also we've got hockey stick sums here. Each digit on the diagonal is equal to the number off perpendicular or to the right or left of that diagonal. There's also some triangles and Lucas numbers and different phenomena here, as well as the expansion of regular polynomials. We've got each of the terms in each row is equal to the coefficient of that polynomial. So the Pascal's triangle is not really related to our math induction problem here, but it is full of interesting phenomena, including Fibonacci numbers, which are given by 1, 1, 2, 3, 4, 5 for the first 5 terms. And basically what we're saying is that any nth term is equal to the sum of the previous 2 terms. And so what we want to do is prove the sum of the finite arithmetic series of n numbers, of n terms of the Fibonacci series, is equal to that last term, 2 terms beyond that last term, minus 1. So the sum of n terms in the Fibonacci sequence is equal to the sum of the next 2 terms, minus 1. And so remember, in order to prove by math induction, we've got something like this. So we've got the next term, sum of the next term, and the sum of n terms plus 1 is equal to the original sum, and then we're going to add to that, in this case, f sub n plus 1, which is the original last term on the left, substituting n plus 1. And so what we're going to do here is we're going to take that original right-hand term and we're going to substitute n plus 1 for n. We get n plus 3, because n plus 1 is n plus 3. And then we're going to take the original right-hand term again, f sub n plus 1, minus 1 here, and we're going to add to that, substituting n plus 1 for n, there. And these cancel out. What we end up getting is f sub n plus 3 is equal to f sub n plus 2 plus f sub n plus 1. And that looks correct given our definition of the Fibonacci sequence, which is the nth term is equal to the sum of the previous 2 terms. And so if this is the nth term, this is the term we're looking for, that's equal to the sum of the 2 terms before it, which is what we have here. And so we could say that if that's our desired term, then we know that that term minus the term before that is n minus f sub n plus 2, and the term before that one is f sub n plus 1, or f sub n plus 3 minus 2. So that one checks out. Right, next, proved using math induction that the product of these 4 numbers is a multiple of 24. Well, we've got the product of any 4 consecutive integers. Right, because if we've got some constant plus 1 plus 2 plus 3 plus 4, that's just the product of any 4 consecutive integers. Remember that multiples of 1 come every number, multiples of 2 are evens, and if we have 4 consecutive numbers, then we have 2 evens, and so we've got 2 multiples of 2. Multiples of 3 come every 3 numbers, so if we have 4 consecutive, we've got 1 multiple of 3, and then multiples of 4 come every other even number. And so 4 consecutive numbers has 1 multiple of 4. And so let's just say that n equals 1 for a test case here. Then we get 2 times 3 times 4 times 5, or 120, which is equal to 24 times 5. And so since 2 times 3 times 4 equals 24, we can say that this is true because, again, we've got 4 consecutive integers. We know 2 are even, so we've got 2 as a factor. Right? We're going to have factors 2, 3, and 4 in all of these numbers because multiples of 3, if we have 4 consecutive integers, we're going to have at least 1 multiple of 3. If we have 4 consecutive integers, we'll have 1 multiple of 4. We'll have exactly 1 multiple of 3. We'll have 2 multiples of 2, 1 multiple of 4. 2 times 3 times 4 is equal to 24. And so then every number which follows this pattern is going to be a multiple of 24. Next one. Prove that the sum of the digits of a 3-digit number is divisible by 9. The entire number is divisible by 9. And so let's say we're going to let n equal a times 100, working in the decimal system here. And so we've got a hundreds place, we've got a tens place, and we've got a ones place. And so if a plus b plus c is divisible by 9, then a plus b plus c is a multiple of 9, or 9 times some constant. And then by algebra, we can move b and c over to the other side. We can say, or sorry, we can move b and a over to the other side. We get c is equal to 9k minus a minus b. And then we can take that and substitute. So n is still equal to 100a plus 10b plus 1c. Or we could say 100a plus 10b plus, and substitute c for 9k minus a minus b. And so then that's equal to 99a plus 9b plus 9k. We can factor out a 9. 11a plus b plus k. And so since this is divisible by 9, of course, then it checks out. And then the next part is prove that if the sum of the digits of a 4-digit number is divisible by 9, the entire number is divisible by 3. Well, we're going to have the same thing, basically. N is equal to, instead of a times 100, we'll get a times 1,000 plus b times 100 plus c times 10. And then we're going to add another value there. We're going to have a d term for our ones place, d times 1. And basically the exact same thing. We're going to say a plus c, a plus b plus c plus d is equal to 9k. And we're going to substitute and say d is equal to 9k minus a minus b minus c. And so we'll go over here. And skipping a step, we're going to get n is equal to 999a plus 99b plus 9c plus 9k minus a, oops, sorry, just that. And then we're going to get, factor out a 9. We get 9 times 111a plus 11b plus c plus k. And of course that's divisible by 3. Any number divisible by 9 is divisible by 3. And so that is true. Next one, any natural number if the sum of the digits of any natural number is divisible by 3, the entire number is divisible by 3. Now we could make an inference or a conjecture. We could do a number of these different examples and make a conjecture, but to prove that we need to show it's true for all cases. And so let's say for an integer, we call it x, and starting with the ones place, so this would be the rightmost digit, a sub 0 times 10 to the 0, which is our ones place, plus a sub 1 times 10, that's our tenth place, plus a sub 2 times 10 squared, that's our hundredths place, and then carrying that out to whatever place we're carrying it to, so it is any number of digits, so it'll follow that pattern. And so the sum, S is the sum, and that's equal to a sub 0 plus a sub 1 plus a sub 2 plus dot 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 a sub n. And so this might run counterintuitive for a moment, or it might not be the simplest thing to intuit for the moment, but it'll come back on us. X minus s, so we're going to take the number minus the sum of the digits, and that's going to be equal to a sub 0 times 10 to the 0 minus a sub 0, which is nothing, plus a sub 1 times 10 minus a sub 1 plus dot dot dot. And so again, we're just going to have x here minus, right, x minus s. So this term minus that, this term minus that, this term minus that, all the way up to a sub n plus a sub n times 10 to the nth minus a sub n. And then that is going to be equal to a sub 1, we're getting rid of that first term, a sub 1 times 10 minus 1, or times 9, right? So a sub 1, whether 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10, so we got 50 minus 5, right? If a sub 1 is 5. 50 minus 5 is just 5 times 9. 60 minus 6 is 6 times 9. 70 minus 7 is 7 times 9. Right? Same thing for any number, whether it's in the tens place or the hundredths place. Right? So 900 minus 9 is 9 times 99. 700 minus 7 is 7 times 99. Right? So a sub 2 times 10 squared minus 1 plus dot 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 a sub n times 10 to the nth minus 1. And that's again because subtracting a sub n from a sub n times 10 to the nth is equal to a sub n times just some string of 9s. Right, we're just subtracting 1 from, we went from this 10 to the nth, and we're subtracting from that a sub n, and so it's just a sub n times some string of 9s, 10 to the nth minus 1. And so then any string of 9s, 9, 9, 9, 9, 9, 9, 9, 9, 9, dot, 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 is divisible by 3. Right? That's just, we've already proven that actually up here. And so we could say that, just take it a step further, we could say that 10 to the n minus 1 is equal to 9 times 10 to the n minus 1 plus 9 times 10 to the n minus 2 plus 9 times 10 to the n minus 3 plus 9 times 10 to the n minus 4 plus dot 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 9 times 10 to the 0, or 9, which equals, taking it yet another step further, even though I think we've already proven our point, 3 times 3. 9 is 3 times 3. times 10 to the n minus 1 plus 3 times 3 times 10 to the n minus 2 plus dot 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 3 plus 3 times 3 10 to 0, which is divisible by 3, of course. And so these, if the sum of the digits in a number, any number, is equal to 3, or a multiple of 3, then the digit in the number itself is equal to, or sorry, is divisible by 3. All right, so those were some simple or relatively easy arithmetic mathematical proofs using induction. Thank you.